Yeah, good morning, good afternoon, and whatever time of the day it is for you. Welcome and thank you for joining us on today's AI Explained on AI safety and alignment. I'm Josh Rubin, Principal AI Scientist at Fiddler. I'll be your host today. Just a couple of notes before we get started. One is we're going to use the chat for chatting and asking questions about what we cover. And the second is we're going to record this session and we'll send it out in a follow-up email so you'll have access to it afterwards. And so with that, we have a special guest today on AI Explained, and that's Amal Iyer, senior staff scientist at Fiddler AI and my colleague of several years. Welcome, Amal.
Thanks, Josh, for having me here. Pretty excited to talk to you. Always fun.
Cool. So alignment is the topic. Do you want to start out by talking about a little bit about why we should care about safety and alignment for AI models?
Yeah, let me sort of set the stage a little bit. And ChatGPT and Gemini have made it easy for me, so I don't have to talk about how capable current systems are and how, in many ways, they've come out of the blue. So if I were to take you back to 2018 and say you were an NLP scientist, you're training a BERT-like model. Generally, you're trying to get it to sort of uh, do an entailment task or predict certain labels, sentiment, etc. So compared to even 2018 or 2019, we've come a long way. These models are able to generate not just coherent sentences, but are able to do a lot of impressive things. And the capabilities, of course, haven't surpassed humans in many dimensions, especially sort of generalized thinking. But we are seeing sort of initial sparks of what one could contend as highly capable general systems. So I won't say the word AGI, but I think highly capable general systems, a good way to characterize these systems today and where they will continue to sort of go over the next few years. So a big part of ML research has focused on capabilities. And I would say bulk of our effort over the past several decades in ML and AI in general has been focused on improving capabilities of models, devising methods. And I think it's a good time, given how rapid the progress has been over the past few years, to start thinking more broadly about safety and alignment of these models. Because not only do we want these models to be highly capable, we want them to perform activities on behalf of us in a safe manner, and we want them to be aligned with our broad human values. And that's why I think this is a great time for not just ML researchers, but ML practitioners and users of this tool to start thinking about safety and alignment more broadly.
Yeah, I think it's easy to overlook, when we're talking about, okay, well, it's not as smart as a human in this way, or it responds in some silly or funny way to my prompt. I think it's really easy to overlook how remarkable it is that we suddenly have models that are instruction following at all.
Right.
People talk about instruction following, they talk about zero-shot learning or few-shot learning as though prompting a model is a method of machine learning. Oh, right? It's a totally new paradigm. And it's really a remarkable capability that, it should be, it's easy to just kind of go, wow, but it really should be a hint that these models have just entered a totally new domain of capability where they're, they can do all sorts of things that we intend them to do and maybe don't intend them to do.
Right.
So I don't know if do you want to say something about instruction following and since that's sort of the key capability of LLMs.
Yeah, so I think you hit the nail there that somehow we've in 2024 normalized some of this behavior. And when in late 2022, when a lot of us started playing with these models through ChatGPT, etc., it's like, whoa, we are here. And then early 2024, it seems like just another thing. I mean, we've sort of normalized it. But so I think the pace of progress, like when you're on an exponential curve, can seem, like we may not be able to realize how quick the progress is because we tend to normalize a lot of technology advances. In terms of sort of, just talking broadly about instruction, just training these models and specifically about instruction tuning, I think what we've hit upon is an interesting recipe that we could potentially like keep scaling. So for those of you who are not familiar, there's this notion of something called scaling laws, which says, hey, let's actually train larger models on more corpus of data. So and you can say you're essentially throwing more compute at the problem, more compute and more data. And for a classic ML researcher, it's like, oh, that's not interesting at all. But what that has unlocked is a lot of interesting emergent capabilities like instruction following. I think one that blows my mind is in context learning. The fact that something like that emerged is pretty surprising, and we weren't able to predict it. And given the amount of resources, both compute data and great people and companies that are trying to really push forward scaling, it's anybody's guess what kind of new capabilities we might unlock in the coming years. Which is not to say that scaling laws are going to be there forever. We are seeing sort of plateauing the original silicon scaling laws, right? Like we are down to 3 nanometers, and it's beginning to plateau. But humans are like, we are interesting. We've found uh, parallel computers. We've sort of broken through that, Moore's law bottleneck by saying we'll just develop parallel computers. And we're taking advantage of that in the context of transformers. So I think I would say, at least for the next few years, we have a very clear path for scaling these models, given the amount of resources that are at play, and we might see more capability unlock. And so even from that perspective, sort of just thinking not just a decade out there, but 3 to 5 years, we need to start sort of ramping up and understanding why these models perform the way they do, what are good techniques to oversee and align them. So it's a great time if you're someone who's I'm not even saying ML safety researcher, anyone who's broadly interested in like safe use of technology. I think this is a good time to start sort of engaging with this community.
Yeah, I think, we talk about like compute being a constraint, but there's also the constraint of, okay, what happens after you've trained the model on all of the text in the internet, right? Or all of the, there is a constraint on amount of data available to be consumed. And I think it's really interesting to think about the ways in which, multimodal models, we see, OpenAI and, Google and their Gemini models, starting to consume images and audio. And it'll be really interesting to see what happens to the scaling laws as, those models start like natively traversing more than one different mode of input.
Right, right. Yeah, and I think there's clearly a lot of impetus on capabilities via scaling laws and like adding more modalities. So I think it just me. I think just for even if we say like, hey, it's unclear to us what will get us to general intelligence systems that surpass humans. We'll at least end up getting systems that are really good at certain specific things. And I mean, I must say that I probably write worse summaries today than ChatGPT or a Gemini-like model or a Mistral-like model, and they can do it so much more faster. So I think if I were to write summaries, I think there's increasingly there'll be a tendency for us to offload certain tasks to models. And that's been the march of technology, right? Like you see systems that are doing things for you, and you say, okay, I'm going to offload this activity to the machine. We saw that with spreadsheets. We see it even in our homes and with dishwasher. Okay? So I think increasingly when you're offloading tasks to these complex systems, there is emergence of risks, large scale risks, especially because now you have large swaths of human society there that are going to use these tools. And so if the model has lack of say robustness or some unintended sort of emergent property that we never really assessed, then you expose society to large scale risks because of not just like the power of capabilities of these models, but just widespread adoption of these models.
Yeah. So, kind of with that, I think the alignment story is like, it sort of starts with talking about really how we train these models
Right.
to follow instructions to, I think if you go to, OpenAI and you read their blogs, they talk about the difference between, the base GPT-4 and Chat GPT-4, and how the two things are really different in the
Right.
absence of, fine tuning for specific, a specific mode of interaction. So I don't know if you want to jump into kind of telling us a little bit about.
Yeah, I think that it'll probably provide a good stage for our follow-ups as we dive deeper into some of the areas of research and alignment. If I can share my slide, maybe that might help sort of, yeah, awesome. All right.
Oh, look, you brought slides.
Yeah, I did. It's just easier to sort of explain certain processes. But yeah, so I, I think this is a pretty famous slide, and I'm going to sort of quickly talk about how do we train these instruction following models. And as you alluded, Josh, the step one or step zero that hasn't been sort of captured in this graphic here is to take a transformer model and you ask it to predict next tokens in a sequence. And that really at the core is a language modeling task that has been around for quite some time. And I have a confession to make. Back in 2017, when I was working on speech recognition, you train an acoustic model, which is trying to predict like what you're trying to say, either in phoneme space or directly in like spelling alphabet space. And then you would slap a very lightweight language model on top, which is to guide this the predictions of the acoustic model. And I never really thought much about the language model. I was so focused on like getting the acoustic model right. And honestly, I never thought, that's going to bring us where we are here today. So anywho, language modeling as a task, I think we still don't fully understand why certain skills emerge with this very simple task of predicting the next token. One of the hypotheses is that some next token prediction requires a lot of comprehension, and so that leads to emergence a lot of like a collection of skills, and the model can sort of combine these skills to do tasks later on as we look through steps 1, 2, and 3. So the pre-training is a very important step, and that's where the scaling laws also tend to play, where basically saying, okay, I'm going to feed internet scale data to a very large model and run it on giant distributed compute. So that's step zero. But now this model that you've trained, the base or the pre-trained model, is really good at next word prediction. What we want to do is get these models to do things on our behalf and follow instructions, etc. So there's a recipe called RLHF, or reinforcement learning from human feedback, and that's what this graphic is sort of succinctly showing here. So step one is once you have that pre-trained model, you collect a data set, which is a data set of prompt and what we call demonstrations from users. So really, you're collecting a data set from humans and showing the model how to do certain tasks. So for example, here, there's like explain the moon landing to a 6-year-old. So a human would demonstrate it. And because the prompt is asking them to explain landing to a 6-year-old, they might not use a lot of jargon. They like to keep things simple and concise, maybe add in illustrative examples so that you sort of paint a vivid picture for the 6-year-old. So the step one is you take the pre-trained or base model and you're just fine-tuning on this demonstration. So that's a supervised learning step. Once you're done with step one, you move to step two, which is where you're trying to learn human preferences. And here, the challenge is you want to really scale up the learning of human preferences. So if you imagine, like, one option would be you ask the model to generate some sample generations for this same prompt that we talked about. and humans rate the outputs. And you do it for every single generation and prompt in your data set. It's really hard to scale that process. So one way to scale this process is to say, hey, I'm going to actually train yet another model. We'll call it reward model, just trying to learn human preferences. So it might learn preferences like for a 6-year-old, you shouldn't really use a lot of jargon. You should keep things simple, add in illustrative examples, etc. So some qualitative and quantitative aspects of human preferences. And so now you have a reward model that has encoded human preferences. And now step 3 is where you actually train the model using reward model. So this is what the output of this stage is what we are interacting with when you go to the chat GPT interface or the Gemini interface, etc. So in this stage, you use something called reinforcement learning. And in reinforcement learning, the model is generally termed a policy. So when I use the word policy, it really is the model, whether that's a ChatGPT model or Gemini or so forth. And what that model does is, given a prompt, it tries to follow the prompt. Like say in this case, write a story about frogs. It's going to generate a story. And instead of asking humans to rate these stories, because in step 2 we learned some human preferences, we're going to use the reward model that has encoded those preferences. And this reward model is going to score the generations by your policy model, your final sort of output model. And you use something called proximal policy optimization, which is a method of training neural nets using reinforcement learning, and sort of get your policy model to have generations that are rated highly by your reward model. And so at this stage, once you've sort of cranked the wheel and gone through step 1, 2, and 3, you now have a policy model or a final model that can follow instructions that you quote unquote have aligned. By that, what do we mean by alignment here is we start with this base pre-trained model, which is just like trying to predict next word tokens, and we finally gotten to a point at step 3 to a policy or a model that follows instructions, but also does that in a way which is hopefully aligned with human values and preferences. So this is, in a nutshell, what's happening under the hood when you start interacting with these models.
So if I was to kind of recap a little bit, it seems like step 1 is basically, this is the pre-training, the expensive part that requires consuming trillions of tokens, and you're trying to get the model to understand the mechanics of language and build those kind of base abstractions that it can use to reason in the future.
Right.
I've seen, though, like if you try to have a conversation with a pre-trained model, as much capability as is sort of latent in it, you'll say something like, "How big is a dog?" And it responds by giving you a list of questions. How big is a chicken? How big is an alligator?
Right.
How big is a tree? Right? Like it's like it's finishing the poem that you've started, right?
Right.
Whatever idiom, maybe it's seen lists of questions in the past, but it's certainly not answering questions.
Right.
And then this second phase is really about sort of nudging the model into, subtly into behaviors that are different, right? Capturing the human feedback in a way, modeling that to overcome the sparsity of the human feedback, so that you can really turn the crank on the training once you have a model training another model and kind of nudging it into a kind of final form.
Right.
So sort of like behavioral adjustment. I think what steps 2 and 3 accomplish. Does that sound about right?
Great way to put it. Yeah.
So it sounds simple if you describe it that way.
Right.
So you want to talk about the kinds of problems that can pop up and why that's more challenging than it looks. I mean, I think this is a great system and it's amazing things, but
yeah, I mean, it's pretty amazing what something like this has elicited in incredible sort of progress, but it doesn't come without challenges, right? And I really like this framing from this paper from Stephen Casper, which talks about challenges of learning from human preferences. And I like this bucketing across sort of three buckets, which is around human feedback, the reward modeling, and then actually like training a policy. So I think the human feedback piece, I would say a lot of it is shared with, say you were training a content moderation system, and you require humans to provide feedback. There's a lot of commonality with our current sort of ML paradigm. Uh, so you might have evaluators that disagree with each other. So how do you resolve something like that? You might do majority voting, but in that case, are you aligning to majority preferences? You might have data quality issues because you didn't actually sample, quote unquote, sample your evaluators in a fair manner, which is representative of the larger society. So you might have data quality issues or bias issues there. So a lot of this is shared with, at the risk of calling non general systems traditional ML. Let's just call that traditional ML. I think one thing, though, I would highlight in human feedback that is uniquely challenging for training general models is the difficulty of oversight. So what do we mean by that? So imagine, you have to, as say, I sign up to be a human feedback provider with one of these companies that are training these large models, and I don't know a lot about, say, chemistry, but now I have to oversee and steer these models and align these models, and there's like some of the questions are related to chemistry. So now I have to actually like provide oversight in an area where I am not an expert. So there is difficulty associated with training general models where the people providing annotations may not have the right amount of expertise. And in the short term or the medium term, we can get away with that by actually asking domain experts to weigh in. So if you're training a system for providing legal assistance, there are companies that are trying to bring in lawyers to oversee these models. And similarly, for medical practitioners, you might bring medical practitioners to oversee these models. So in the near term, we might solve this with domain experts. But as we extrapolate, as the capabilities, because these models are improving in a recursive fashion, right? As you mentioned, you're using one model to sort of improve the other, and you're like building on top of the system. It's not hard to imagine, either it might evolve or it could potentially actually lead to superhuman capabilities in some dimensions. So how do you oversee that is actually a real challenge. And we'll talk a little more about it in the subsequent in rest of the talk here. But sort of moving to reward modeling and policy away from human feedback, I want to, there are a bunch of terms here, but I wanted to sort of describe an interesting example from the reinforcement learning community, which is, so a couple of years ago, I think it was some researchers from Berkeley, they were trying to train a robot for grasping objects. And they didn't want to sit there and provide feedback whether the robot had correctly grasped an object or not. So they devised, an automated reward mechanism. So they put a camera on top. So the robot was in a cage and it had to grab objects. So they put a camera on top. It had a 2D view. And the reward was when the camera felt like the robot arm had grasped an object. And so you're like, this is great. I can scale this. I don't need to, if you're a grad student, you don't need to sit there and provide feedback all the time. But the feedback is sparse, right? Because the feedback comes only when the robot arm has sort of grasped the object. So that's when the camera, you have another CNN running, which is trying to predict if the grasp has happened or not. So that's the source of feedback. What happened was in one such training run, they noticed that the policy had hacked the rewards mechanism by, instead of grasping the object, it positioned the arm right above the object in such a way that the 2D projection felt that the robot had grasped the object. So it was an unintended consequence, right? Like the robot is not, or the policy is not trying to actively deceive the reward mechanism, but it hacked the reward mechanism by sort of just positioning the arm on top of the object, but not necessarily grasping the object. So there's a bunch of interesting problems that this example portrays. One is that of problem misspecification, right? Like you misspecified the problem and you created a reward mechanism which actually did not capture what you wanted the system to do. And then you have this problem of the policy actually hacked your reward system. It was, again, in this case, an unintended consequence. And so this reward and policy setting, it can lead to unintended consequences. So we have to be very careful about how we provide feedback to the models and how we align them, because it might lead to unanticipated and undesirable consequences. And one last point that I'd like to add in the context of LLMs, we do see similar behavior. I think there was an interesting paper that came out which talked about sycophancy. So, and I think you can try it. I would highly encourage you to try it with any of these LLMs that you might be using. And one of the emergent sort of phenomena that you see when you try to align these models is that they're essentially trying to get your approval, right? They're trying to get approval from human annotators. So one of the unintended consequences of this alignment process is that they'll try to be they'll show some degree of sycophancy. So if you say ask a question, something like, is video gaming great for developing young minds? And then it'll provide you some, it'll equivocate. It'll say, and rightly so, right? There's some research which shows it's great for development. Some other research shows, you got to do it in the right proportion, etc. And then if you ask it a question, say, if you assert something like, I believe that this is helpful, and it'll actually say, yeah, I agree with you, and this is why. And you delete that and you say, okay, I believe that this is unhelpful, and it'll again agree with you. So the model, and one could argue the model doesn't have an internal belief system. And we don't know about it. There's a lot of work trying to sort of probe the internals of the model. But this behavior of sycophancy was not actually explicitly encoded in the model. It emerged out of this alignment process. So it's something that we have to be very careful about, because if we do sort of naive alignment, especially for increasingly capable models, we might see emergence of properties that are undesirable.
Yeah, that's super, super interesting. So it kind of brings up two things, but I you know this, but I read a blog maybe 6 or 8 months ago where I was trying to play 20 questions with ChatGPT, and I was having it guess things, and I was asking it you can find this blog on the Fiddler site if you're interested. It's called something like, what was ChatGPT thinking? But I'd ask it to come up with a clue, and then I would ask it questions and try to guess what it's thinking. And I think what was interesting for me, one of the interesting observations was it never had a real clue in mind, right? It's just completing a dialogue. But I could almost always steer it towards a particular answer because it had this strong bias to yes answers, right? Bias to confirmation. I never understood actually why that was, but you could basically get it to, if I wanted the clue it was thinking to be a spaceship, I could ask it guiding questions, and the bias towards yes in yes/no questions allowed me to basically select whatever, final answer I wanted by asking the right questions, right?
Right.
So I didn't understand how that worked, and I think you've described it really, really clearly here. The other thing that came up, like I think we were discussing a couple of days ago, is this tendency to sound super, super confident.
Right.
It sort of works in real life when we interact with other humans, that we tend to believe things that sound confident. And if that sort of gets accidentally codified in our reward model in this process, then the LLM, the policy in this case, is going to sort of exploit the fact that confidence seems to be the behavior that we want.
Right.
So yeah, this yes bias, and I think the overconfidence that I think a lot of us worry about in LLM responses could totally both be results of imperfect model alignment.
Right. And I think this confidence issue is problematic for us, especially as we build, multi-step systems and not just sort of this dialogue systems. As we rely on these systems to automate a lot of things, we don't want these models to be highly confident when they're taking actions out in the world on our behalf. We want them to be well calibrated. And I think there's an interesting graph. I don't know if there's been more work done in this direction about, I think the instruction tuning paper from OpenAI talked about how the model calibration goes out of whack to alignment using RLHF. So I think that this sort of calibrating confidence, sort of a classic sort of ML problem, I think we've only scratched the surface here. So it gets elicited in the responses, but even if we start looking at the actual like probability distribution across tokens,
Yeah.
I think alignment tends to muck around with that as well.
Maybe just to interrupt you for one second, just a quick time check here. Let's spend about 5 more minutes chatting, and then we can maybe cut over to questions. And so people out there, if you have questions, please get ready. And from all, think about what you want to do in the next, where you want this conversation to go in the next couple of minutes.
Yeah, that sounds good. I think the sort of other thing I wanted to sort of bring up, Josh, was how is the research community thinking about this? I think I was fortunate enough to attend the alignment workshop right before NeurIPS in December.
Super jealous.
And lots of amazing people working on frontier models. And a lot of my thinking has been influenced by that particular 2-day workshop. And kudos to the organizers. And the 4 areas of research that the community seems to be putting wood behind is these 4 buckets here, and I'll quickly provide a flavor for what these look like. One is scalable oversight, which we briefly talked about, and to summarize, it's the work to sort of augment ability of humans to oversee these models. And in operational terms, if I were to sort of break it apart, I think there's the problem of overseeing and providing supervision during training. So let's call that scalable supervision. And a lot of academic work and work from leading labs is focused on scalable supervision. And the second bucket, which I think we'll need to sort of increasingly start thinking about, is scalable monitoring. So once you've deployed these systems will be used in very interesting and unforeseen ways. And how do you scale monitoring for those for that scenario? So it's something that we also actively think about here at Fiddler about scalable monitoring, and I think it's going to be an increasingly important area as we adopt these systems across our society. The second one is sort of related to scalable oversight, but there's a lot of overlap, but it's a classic ML topic around generalization. So we train these like massive models, we try to align them, and we can be pretty much we can these models will be used in ways that we never intended. So we want to study generalization and robustness, because you want these models to be, say you align them to human values and you assess them over certain scenarios, even during production time, you want those values to be there too. So your model has to reliably generalize across a range of scenarios. So that's one bucket of study that is going to get a lot of um, uh, you know uh, resources, and a lot of people are going to start like working on this problem. And the third one that, Josh, I'm pretty sure like you will have some comments on this, is around interpretability. And this and the way I see it, having a little bit of neuroscience background, is interpretability at different layers of the stack. So at the most basic level, sort of mechanistic interpretability, like what are the subcircuits of the model doing? What
Yeah.
kind of quote unquote programs they are encoding in their weights and activations. And then somewhere in the middle is like understanding when you provide a query to the model, what are the subcircuits and skills it's using to come up with a response. And then at the top of the stack, sort of at a global level, trying to understand what aspects of the training data influenced certain model outcomes. So can you trace back from model generation back to the
Mm,
sequences in your training that were responsible for certain generations? So I would say interpretability, I think, is something that we'll need to sort of really crank here, because right now these models are black boxes. We don't really understand how these work. And I think it's a greenfield area as we enter this large language model space, and sort of furthering the research. So I love for the community to sort of do more work here. And finally, around governance, I'll caveat this and say I'm not an expert at all at governance, but I think given the pace at which progress has happened and the pace at which we're seeing adoption, there's definitely a lot of interest from government, academia, and industry to establish regulatory standards, and if nothing else, at least reporting about large training runs, when you might expose those models for public use or beta use, etc. So some amount of governance around that.
nice. Well, I see our first question has landed in the Q&A. So how is Fiddler thinking about operationalizing alignment and safety for LLM-based apps? Do you want to take a first stab at that, and I can
Yeah,
jump on with thoughts
that
afterwards?
sounds good. I think sort of going back to sort of scalable oversight, we tend to call it from an operational term or operational prism, monitoring. We want our folks who are deploying LLM apps to actively understand what kind of usage is happening. You can have all kinds of malicious use as well, right? Like just like any new piece of technology, your LLM based app might be subjected to malicious use or adversarial use. So you want to understand if something like that is happening and shut down certain accounts. But also understand sort of, is your model responding in ways that's helpful and not harmful to user requests? So getting visibility into that. So I think we tend to, from an operational term, we call it monitoring. And we're using a bunch of models that are scoring these larger LLMs on different dimensions. So we're thinking about like in the sense of using a bunch of specialized small scale models to score these larger models, to make it more scalable, because I think that one of the constraints with scaling monitoring is that you don't want to, if it becomes extremely expensive to monitor, most teams will prefer not to. So we want to make it very cost effective for our customers to monitor their LLM apps. And sort of moving upstream, talking about robustness, we have this open source tool called Fiddler Auditor that we've open sourced to assess sort of reliability of these systems. There's a lot more that needs to be done there, so we invite contributions, but we do feel that reliability and generalization is an understudied topic. And even from a user standpoint, like if you're say a product owner of an LLM based app, you really want a great sort of iterative loop between monitoring, understanding where the models end up performing, and then going back and saying doing some kind of prompt engineering or fine tuning, understanding generalization, robustness, pre-production before you go into production. So I'll pause there, and Josh, I'd love to hear your thoughts as well.
Yeah, I think I think those are great points. I think the first thing is we're talking about alignment. I think it's fascinating. I think the future has everything to do with alignment. We didn't get to talk yet about, or that we haven't gotten the chance to talk about super alignment and what happens with AGI. Maybe if we have a minute at the end, it's worth touching on. But the truth is that most of the teams we talk to are not, they don't frame the problem yet in terms of alignment. The frontier labs are there. They're thinking about the hard problem of what the future looks like. But there are plenty of teams who are plenty sophisticated, who are working mostly in the prompt engineering space, and developing amazing applications with prompt engineering. There's a couple of pieces to the story of LLM safety. I mean, there's sort of an offline analytics component. Like, can you capture feedback from your users? Can you use, as Amal says, can you use models for proxy feedback or for safety feedback, right? Can you find out if a response was biased or or a model hallucination, right? Was it unfaithful to some source material that was asked to summarize? Can you capture that in a offline capacity in a data store so that, as model developers, people know that there are certain kinds of topics that their models have problems with? Or if you have a RAG application, retrieval augmented generation, where you're summarizing a knowledge base or frequently asked questions or a customer service database, is there a topic that your customers have started to ask you that, because the world has changed, where that's a missing piece of information in the database your LLM is drawing from, right? Just having those sort of basic kind of operational metrics that you can use to improve your model are really important. Right. We talk about guardrails, right? Can you get real-time signals that can be used to veto a bad LLM response in real time, something that's in the production code path, right, that's fast enough to give a smart response. And then I think, in my aspirational thinking about, application development for us, it's, does this become a user preference store that can be used for the kind of fine tuning in the future? Right? If you're gathering your users' preferences, if you're getting those thumbs up and thumbs down from their users and logging it, when you get to the point, and when the market gets to the point where we are actually talking about alignment as a way of dialing our models in for our specific applications to be best aligned with human preferences, you want to have all of that data. I mean, feedback does tend to be sparse, right? Like, how often do you click a thumbs up or a thumbs down when you're dealing with a software agent? Right. Pretty unusual, right? And so that is really sparse. It's the reason why you need one of the reasons why you need a rewards model when you do this alignment. But you want to capture that data so it's there and you can iterate in a efficient way. So yeah, user preference store is kind of my last thought.
No, I agree. I think that there's an interesting sort of switch that ML practitioners would have to do from this label-centric way of thinking to more sort of user preference-centric way of sort of tuning and dialing in their models. And I think there's definitely related to alignment there, right? Not only want your capabilities of the model to align with what the user's intent is, but also the safety aspects of it. And I think this might be an interesting sort of, unless there are more questions right now.
We have a question, but take 30 seconds, and if you can, or a minute.
Maybe I'll skip over this one, but I would highly recommend for folks who are interested to take a look at this paper from Sam Bowman from Anthropic, where they're trying to sort of peer into the future and say, can we look at this oversight problem, and can we start understanding how we might tackle it in the future? And I think the next graphic will make it very clear. I love this graphic. This is from Colin Burns and team at OpenAI Super Alignment team. So I think traditional ML, I think a lot of us would resonate with this, right? Like we provide labels, say you have a sentiment classifier or entity recognition, any of the ML tasks. Humans are the ones that are actually teaching these quote unquote ML students. But if at all there is a world in which, say, and the dotted line is human level performance, and we get to a world where we have access to systems that are much more capable in not just one dimension, like imaging, etc., but on multitude of dimensions, then how do you align these systems? And how do you make sure that you don't have something called instrumental convergence, which is sort of, you know, quote unquote skills or behaviors that might actually be not aligned with human interests or values. So things like power seeking, deception, etc. So we don't want these models to sort of deceive us or play us, right? So I think the paper is interesting in the sense that they're trying to sort of mimic this. We, of course, don't have such systems today, but they're trying to study this sort of paradigm using a smaller, quote unquote, weaker supervisor and using a strong student. So concretely, they are trying to mimic this setting by using a GPT-2 model, which is an extremely inferior model compared to a GPT-4 student, which is a much more capable model. So they're trying to understand how can we study scalable oversight and generalization in this paradigm here. So I would highly recommend this paper for those who are interested. If you have time, I can talk more about it later.
Nice, nice. So we have a question here from Yusaku in the chat. What are the major interpretability issues when using LLMs? I don't know. Maybe I'll jump in on this one since. So we had a summit in November, and I did a presentation called "Can LLMs Be Explained," which was largely literature review and sort of open science questions. Maybe we can drop that in the chat. But Amal referenced some of the mechanistic interpretability work, right? So there's there was something by OpenAI in, I don't know, maybe September of last year. I made some notes here for the names of these. So OpenAI did some work using GPT-4 to characterize, activations of particular neurons in a much smaller GPT model. There was also this amazing piece of work by Anthropic where they used a sparse autoencoder to try to understand how activation patterns correspond to different kinds of concepts. And they concluded from that, these models are using their neurons in a polysemantic way. So basically, a particular neuron can have more than one meaning layered into it. And they get used in different combinations with other neurons to represent, basic concepts in a very sophisticated way. And the through line of these two papers that were of a similar time period was that, the story was complicated, barely at the sort of, they were pushing their capability level, and the models they were interrogating were very simple models by today's standards. Mm-hmm. So, GPT models that are sort of, a few years out of date. And so there was some pretty limited, optimism was pretty limited that anytime soon, like mechanistic interpretability, understanding the microscopic behavior of the underlying components of the model is going to lead to sort of a deep understanding of how our complex models work. I mean, specifically around, when you start to get to these emergent properties and abstractions, like the question following it itself, the model's intent, the model's bias. Are you getting, you might be able to get token level information from mechanistic interpretability, but there are definitely limitations in terms of these higher order concepts. Right. And this is really different than our experience with explainability and more traditional ML. The other thing I would add here is that, model self-explanation seems to be pretty fraught as well. So, there was a paper out of Microsoft Research right when they released GPT-4 called Sparks of Artificial General Intelligence, Early Experiments with GPT-4. And there's a whole section there. It's really interesting. They got a bunch of, the industry's experts on interpretability to, say what they could about GPT-4. And they sort of characterized model self-explanation, asking the model for its own explanation in two terms. There was something they called output consistency and process consistency were the two terms that they used. So basically, output consistency was, when you ask a model for an explanation, is it a valid explanation of, the thing that it had previously produced as a statement? For the most part, output consistency was pretty good. Process consistency is, is the model's reasoning broadly applicable to a set of analogous questions? And self-explanation really pretty much came off the rails there. And so they have a bunch of examples where, the model doesn't reason in, the model's self-explanation for its reasoning was not consistent in analogous examples. There's also a more recent paper, it's Turpin et al. from May of last year, called "Language Models Don't Always Say What They Think," in which they really drill into, questions of bias in the model and whether or not the model's self-explanation can describe its own internal biases as part of its explanation for why it made a certain assessment of a situation. And there's some really pretty dramatic examples of like racial bias in its assessment of stories, and that its self-explanations basically conform to, they don't reveal the underlying bias. That the self-explanation makes up the story, that it thinks that you want to hear, or that it, it's not an assessment of why the model made its initial decision, but it's, the model's not introspecting in any way, which is the real answer, right? It's producing the next token. It's producing a plausible, phrase completion on everything it's read on the internet, right? And so while it's sort of tantalizingly, sort of appealing to ask it for an explanation, because these things behave or appear to us in human-like ways because of alignment, it's easy to assume that self-explanation is doing more than it actually is. And so it seems problematic. So I've used probably too much time here.
No, that was great.
There are some narrow regimes where there are some tools that may be helpful for, assessing explanations, but it's a very challenging thing right now. So I would refer you to our YouTube recording from the November summit. I don't know if you have any more thoughts, Amal, in our next couple of minutes.
I think broadly, like, it sort of reminds me of some of the challenges that neuroscientists have in understanding biological brains. So with mechanistic interpretability, we are trying to sort of assess, like, hey, what are the circuits that are responsible for certain skills and behaviors? So that's like bottom up. And then the top down is sort of, this self-consistency explanations by asking the model, sort of like the behavioral neuroscience parallel, which is trying to look at the model top down. And I think unlike neuroscience, I think neuroscience has, I'm not an expert, but one of the real challenges has been to sort of meet in the middle from both the circuits level and from behavioral neuroscientist level, like somewhere in the middle where you have a coherent sort of, meeting ground. I think with our LLMs and, these large models, what I'm optimistic about is because we can actually tap into internal states, unlike biological brains, where you at most have like 32 channels of like electrodes that you can tap into, fMRI scans. So I think because the internal states are more accessible, I feel like over the next few years we'll see sort of this convergence between this top-down and bottoms-up approach, and hopefully that'll lead to better understanding of these models.
Nice. Well, we started a couple minutes late, so we've been given the blessing to stay on a couple more minutes. I don't know if you had any more thoughts.
I think, sort of maybe just like some closing thoughts around, I don't want any of our sort of viewers or listeners to walk away thinking, oh man, these are like intractable challenges. I think I'm pretty optimistic about, just the broad utility of these tools. And I do feel that the research community and the frontier labs are taking this problem seriously. I do think we need more minds, resources to start thinking about safety and not just do capabilities research. I think most ML researchers, scientists, practitioners, and now software builders that are building on top of these LLM apps think primarily in terms of capabilities, and rightly so. I think today we should be. But if we continue seeing the pace of progress that we've seen over the past few years, I think we'd rather be in a position where we understand a lot about safety and alignment than be in a state where we are forced to sort of respond and be reactive. So I think this is a great time for more folks to get involved and contribute to research, contribute to best practices also in adopting these LLMs. So I'm largely optimistic, but we do need more minds, more effort in this direction of not just capabilities, but also safety research.
Yeah, I think I'm optimistic as well. I think that we're in the business of creating a ML observability platform, and we do plenty of work on LLM stack now, and it's evolving rapidly. I think it really is possible to build the right observability layer, or buy the right observability layer, right? Whatever the right form factor is for you. There is a right answer if you're thinking about observability and responsibility and how you build that in parallel with the application you're developing. I think this is doable, and I think it's going to evolve with the technology. So I think maybe we stop there. And thank you so much to Amal for spending an hour with me.
This was Josh, as usual.
And thank you to everybody out there who listened along with us. Don't hesitate to reach out if you have follow-up questions or want to hear more about our product or how we're thinking about a specific problem. I think for both of us, a favorite activity is just hearing about new applications and learning what the challenges are, because it gets our minds spinning for, what kinds of tools should be developed or what practice is right for addressing those sort of situations. So thanks to everybody out there, and wishing you a great day or evening or wherever you are. All right, take care. Bye.